The slides are available online if you want to follow along. I like to follow along the slides when I listen to talks. It makes me be able to go back at my own pace. But if I ever go too fast, if you have questions, let me know. That's the advantage of having this format, having a smallish conference room. You can ask questions along the way. My talk should have time for questions during the course of the talk. So preface, regular expressions are kind of a ubiquitous tool in programming. Most people who program have been exposed to regular expressions, no matter where you're from. You use them in Perl, Ruby, Python, wherever you are. Even a lot of people in Haskell use regular expressions, even though it's kind of a taboo thing. A lot of people do it in private or in their own libraries. It's not a bad tool. So let's go over people who don't know what a regular expression is or aren't familiar with it or need a refresher because maybe you grew up in Haskell and you never were tainted by regular expressions. One looks like this. Is this readable for everyone in the room, the font size? So you kind of define a pattern to match on. It's a tool for matching patterns and strings. People use them to validate emails sometimes or to validate forms. This expression would match on either an A or a B. That's what the pipe says. Either an A or a B, many CDs back to back, 0 or more, and finally an E at the end. So this is a little diagram that kind of illustrates what it looks like. When you start, you have either an A or B. You have many loops of C or D, and again E at the end, and then that's success. So this pattern, this very expression, would match on some. Oh, I keep using this keyboard. Would match on something like AE, right? It would match on the A. It will go down that branch, and then match on E. It will match on A, CD, CD, CDE. So just get an A and then loop around many CDs, 3 CDs, and get to E and then end. It will match on B, CDE because you go on the B branch, 1 CD and go to the end at E. But this one wouldn't match A, CD, CD because there's no E at the end. We need the E at the end. Or A, B, C, D, E. A or B, not both. And B, C, E because you need both the C and the D for it to work. So this is kind of an example of our expression. This isn't anything too deep in the talk. This is kind of, if you want a refresher on what this expression means semantically, it's either an A or B, then multiple C and Ds back to back, and then an E to end off. You need all 3 components for this to work. Or technically, one's required, and this one is optional, and this one's required. One thing a lot of people do in different languages, in Ruby and in Perl I've used, are things called captures, where you can capture, where you can access the where on the match you can access each parentheses. So for example, if you have a language that supports captures and expressions, you can get what's in the parentheses out to use programmatically. So it's useful if you're validating an email, you can get the domain, you can get the username, you can get the ending thing, the TLD. So these are ways that people use regular expressions in other languages. They use them, they match on them, and they can extract things based on using regular expressions. So regex are just not only a way to match or to test strings, it's also a way to extract information from strings. So matching and extracting is kind of how people use regex in the real world, in real life. So this talk is about something called applicative regular expressions. This is generalizing the capture system to be indexed, to be something you can access as a type. So applicative regular expression is regex where the type is in the, so the type of result is in the type of the expression. So a regex string would be a matching capture, we would capture a string. A regex int will be something where we capture an int. So for example, if we have defined these things, we can have a car could be a function that gives a regex car, which is a regex expression that matches on a character. This expression that gives us a regex that matches on a string. So the benefit of this is that if we run our regex on a string, we get the type we can use safely, type safely, right? So if you notice the type index here, I'll use my mouse. So the type of the expression supposed to result is the type that we get in return. This benefits us because we can use the types. We can have an int. We can know we get an int that we can use in Haskell to pattern match on and use it as an int. In captures regularly, it's not type safe. We get a string or something in return. But in Haskell, the benefit is that if we parameterize our expression by a type, we can use that type information and use it as that type. Regex int will give us a maybe int. Regex double will give us a maybe double. And just an example using these combinators that I've defined that we'll go over later. This is kind of our end goal, be able to find this reg expression. So this is a applicative syntax, applicative style Haskell code. People who've used maybe partial combinators may be familiar with this syntax or with this type of the style of writing code. We tuple together a matching of car A or car B along with many strings and the car E. This is exactly the one that I showed at the beginning of the talk, but translated to applicative style. And so this gives us, if we apply this to run regex, we get maybe car string. Note that the type here is the type that we get to use it later on. So if I know it's a string, a car and a string, I can use that and pattern match on the tuple and do what I want with it. So this is the benefit of the applicative regular expressions, type index, an example of how we would write something in this style and our eventual goal. So it's an example of our eventual goal. We can run it and get on A and get just a list, run it on A, C, D, C, D, E, get just A, and then the many matches. This is the porting of the captures behavior into Haskell. So this is what we want to do in the end, preview of the end goal. And no match would give us nothing. One thing nice about Haskell is that if they make us a functor, ideally, we want to make the functor, because it's applicative, we can even map values, map functions that should be linked to the results, and we can actually get like an actual data type out of it. We can parse, and also we can do parsing while we match it. So this is kind of also common applicative style Haskell code, but just it says match on car A, but we place value as false. Match on car B, and place value as true. So A would be false, B would be true. And when we do the many, we get the length out of it. So instead of getting the actual list of strings, we get the length out of it. So an example of how they can use the interface. If we had this interface built and running, we can use it this way. This is the advantage of having applicative style. We can get not only the matching, but also we can process the result in the end. So this is kind of a preview of what we're going to do, and we're going to do it in a little less steps than you might think. It looks a little complicated. Like if you think about how you build this, you might start with processing strings and lists and matching characters. It's something that isn't too obvious how to start doing, but we're going to take a step back and look at what's going on and look at the overall structure of what we're trying to present. And from that, a self-evident solution will arise out of this. So what is the regularity about? So why is it called regular expression? Anyone know why it's called regular expression? What's the regular come from? Anyone in the audience? Yes. Exactly. It's a regular language, which is a mathematical structure. We're going to simplify it a little bit and say that a regular language can be inductively defined from 3 base elements and 3 operations that are subject to some laws and how they are equivalent. All regular expression needs an empty language that fails to match on anything, an empty string which always succeeds and consumes nothing. A literal matches as a given car, so literal A will always match A. And you always concatenate them, alternate them as in a choice, or repeat them 0 or more. So this is a mathematical construct that if we have these 3 bases, elements, and these 3 operations, we have a regular language with some equivalence constraints. This is what regular is. But if we look at it, a lot of it does look a little familiar to a lot of structures. So if you use Haskell, some of these terms start looking a little familiar. You might see them in different contexts. And I want to give an alternative perspective. There's the pun there. The type class in Haskell, applicative, is pretty common. We have this operation called pure, which always succeeds. We have a operation called concatenation, which has A then B. or this person, that next. And also, if you look at base, you'll find another type class called alternative, another very common type class in Haskell. It has these three things. It has an empty method, which is an always failing method. We have an alternation method, which is this or that. Notice this is this and that. This is this or that. We have a repetition operation, which takes an FA and returns F repeated many times, the value repeated many times. We kind of squint at this. This looks a lot like, well, I kind of framed it in the way to make the hint, but it looks a lot like what we have needed in the regular expression. So if we recap again, so what was the regular expression I said? There's three base operations. There's the empty language, which looks a lot like empty in the alternative. This also isn't a coincidence, but we're seeing that the things match up pretty well, a little bit too well. We have the empty string, pure x, which is the operation that always succeeds no matter what and consumes nothing. We have, so we need a literal operation, but this isn't in those things. You know, I don't have 5 things, we need 6 things. So this part we can leave blank. This is the missing part, the hole in the regular language. The hole that applicative and alternative can't fill. Concatenation we can fill with, call it app, the star operator. Alternation we can fill with the type, the alternative or choice operator. And repetition we can fulfill with many. So what we did here is that we knew that we needed these 6 things to implement our language. We noticed that these type classes in Haskell that are very common, very, very common in Haskell, seem to somehow magically fulfill 5 of the 6. They match perfectly almost. So this is a process. So in this talk, we're not really talking about implementing this thing directly. The real thing we're looking at is how we can look at a problem and solve new problems this way. Our problem, our structure, we need these 6 things, and this type class has exactly the 6 things we need, minus 1. So the process is look at our problem and see what we need, and see that this thing has all of that except for one integral part. So what if we could take a literal just as the own literal type operation and give it the rest of the picture? Well, if there's a way if I had a literal type, give it all the other 5, then I would have a full regular language. So this is the style. So we define our primitive type and then add the structure we need. This is kind of the big picture of, I call it functor combinator style. There's a lot of ways people call this. I like it because we take a functor, we call it prim, and we add the structure we need. And the structure, if the structure we need comes from a type class, we can always use the free structure of that type class. So we notice that we need exactly these 5 things to add to literal. And these 5 things come from a type class. We can use the free structure of that type class to get these 5 things for free. They come automatically using a functor combinator. So this is the full process. This is from the free package in the free alternative. The free package has a lot of different free structures for different type classes. It has free structures for monad, applicative, alternative, comonad. Oh, that's actually a co-free structure. So this is given to us in the library. And then notice that for any input, so I call it functor combinator because it takes a functor and returns a new functor. So alt F is itself a functor. And then for this, we also get these instances for free. So for anything we put into F here, that thing has an alternative instance. So if we put prim into this structure, then prim has an alternative instance. And it has all structure we need. So let's make a type. This will define our literal primitive. This prim A will match exactly on a certain character and return a value type A. And now our expression is alt prim. And we can define a primitive saying we lift car C will be lift alt, which lift alt will lift, this should just mean A here, sorry. We'll lift primitive into alt prim. So what we did here is we define the literal character, the missing piece, and by putting into alt prim, we gain all 5 extra things automatically for free. And now it has all operations, right? Because if we have alternative, we have here, we have empty, we have alternation, we have many, we have all these here. So with this instance, we have all these for free because this is defined in the library. We now get empty works perfectly. We have pure, we have car, which we just defined. We have sequencing, we have alternation, we have many. All that comes directly from using regex, from using alt. Remember, regex is defined as alt prim. So by putting prim into alt, we get basically all the instances for prim for free. So we can now sequence prim, we can now fnap prim, we can now alternate prim, we can now get an empty prim, we can now get we can now have a many operation for prim. So all these functions that come from our type classes we get for free. And you notice 1, 2, 3, 4, 5, 6. This is all 6 elements. And we have a full regex type. Here's some examples of using this type. It's really nice to do string. We just need a traverse car. This is kind of comes from the magic of applicatives. You can define digit just as a useful combinator. Because regex is applicative, we can traverse it. Because alternative, we can use asum. Asum is an alternative method that tries all choices and then gives you the first choice. And we have all operations now work automatically for free just because we gave it to regex. Did you see you gave it to alt? We transformed it using free combinators. So this is the whole thing, pretty much. I told you it took less steps, so it just took 1 step. All it took was this primitive, this car. We have our whole regex system. We can build regex we want. Everything I said before now works already. But it's a little anticlimactic because what do we want to do? We want to parse it, right? The point is to be able to parse and match on things. So now we can build our regex expressions. How do we use it to parse things? How do we parse things? Well, there's 2 ways to kind of use a free structure. 2 main ways. One, you can interpret it into an instance. You can offload the logic. I'm going to say this looks a lot like using a list using fold map, which we'll go into a little more deeper later. Or we can pattern match on the free structure and just use normal Haskell 101, just pattern matching, recursion, just basic Haskell techniques. Using a list, using pattern matching and recursion. So these are 2 ways we'll look at how we can use free structures, how we actually use them. These are 2 main patterns we can use. We'll go over both of them. First, to go over the interpretation, we had to ask, what is freeness? I glanced over it. I said that this gives you all the structures for free. Freeness is a property that, here's an example of a free monoid, or approximation of a free monoid. If I tell you that list is a free monoid, it takes a type from the type. That new type, so anything you give to a list is now a monoid. So now list, you can now append, so that if I have a list of cars, I can append the cars, I can get an empty list. And the free list, and for a list to be a free structure, it needs these 2 operations. It needs to be injecting into it, or we need to be able to run it out using into a final accumulating context. This structure defines what it means to be freeness, means to be free. We can always put any type into our free monoid type, and we can run it into some target monoid that cumulative for us. So doing run fm on f would substitute every injector fm for f. It's a little abstract, so let's look at a real example, an actual example. Oh yeah, so anyone guess what these are for list types? Inject fm is the robot monkey operator, and run fm is fold map. So let's look at an example. So int is not naturally a monoid in Haskell, right? If you do int, if you 3 append 4, you get an error. But if we do free monoid int, we get a free monoid instance. So now we can use int as if it was a monoid. So this is kind of using we can inject one append to empty, append to inject inject two. It should be inject FM, sorry. Inject F3, that's F4. So we're using int as a monoid, even though it's not a real monoid in Haskell. We give it monoid ability, monoidness, just because we give it to the free monoid. So what does this give us? It gives us the ability to, in the essence, defer what our appending operation is until later we want to use it somehow. So we can use this and interpret into sum and get a sum of the three using full map sum, which replaces all the empties with 0 and all the appends with plus. We can use it with full map product, which replaces all the empties with 1 and all the appends with multiplication. We can even use it with something like max, and this replaces all the empties with min bound and all the appends with max. So in using the free monoid, we can use it by picking a monoid to target and run full map, or the running function will put our thing into that target. Replace all inject with the function. So we can choose how to interpret the list, how to interpret the int. So remember, normally int doesn't have a monoid instance, but if we give it the free monoid, we can now use it as any of these monoids we want later on. This is what freeness means. Was that a question? No. So how does this work with our alt type? So alt has the same interface. We can lift something into the alt, we can inject it, or we can run out, we can fold it. So lift alt is the analogy of actually alt FA, typo there. Lift alt is the analogy of the injecting, and run out is the analogy of fold map. And when we do run out, we substitute all lift outs for the function we want to substitute in for. So in this style, if we want to do this interpreting running style, this folding style, we want to think what alternative gives us the operations we need. We're basically offloading our operations onto some alternative, and some concrete alternative. And in Haskell, there is one that seems to match perfectly. We need an alternative where prim A can represent consumption, consuming the next character. We need an alternative that has star will sequence consumption. We need an alternative where alternation means backtracking. So if we can find this alternative, then we can run our regex into that alternative, and it'll give us the right result we need. And this alternative exists in Haskell already. It's kind of convenient. It's called state t car maybe. State t list car maybe. We can interpret prim A as a function of state. We can, and state t, the star sequences function of state, and alternation is backtracking of state. So this already is how state t works. It's really convenient. And so we can run it. We can use, if we can provide a process prim function, which processes a prim into state t, then we can run it like this. We can do run out process prim on the regular expression, and we get the actual function. So remember, run out will inject the process prim into every time we use lift out. So I'll run this prim, so run this function to kind of help us get out of the regular expression. I'll go more on this concretely later. But does this work? First, let's make sure it works. And it does work. It does work exactly as we said it would. So just that's it. It was kind of weird because we didn't do that much. This is all we did. This is the whole code that we wrote. So it's less time. I actually, when I first started this, I actually wrote it out as a tweet. It fit into one tweet. I wrote it at first. So this is a full regular expression system with parsing, matching, and everything using the free applicative. I'm using the free alternative. But let's take a step back. This kind of looks like cheating, right? Because who implemented the backtracking? Who implemented the state machine? Who implemented the sequencing? What happened was that all the alternative functionality was implemented by state t. Whoever implemented the transformers library did all that for us. all we need to do is provide the process prim for the to interpret the prim. So components 1, 2, 3, 4, 5 were handled by state T, and we implemented the sixth missing piece. So in a way, it's state T did 83% of the work, and we did 17% of the work, 1/6 of the work. But really, it makes sense because state T gave us, or alternative gave us 5 of the 6 parts of our question, and we provided the one missing piece. So this is saying that if you can provide the one missing piece, alternative will handle the rest for you. That's kind of the nice magic of it. If we provide just how to handle the primitive, then state T or applicative, the alternative, free alternative, will handle the rest for you. Right? So we knew how to handle the one thing, that's our job, and then the rest of the abstraction handles the rest of it. So that's kind of what's free is that in handling the one thing, we get the other 5 things for free. And the other method is a little more basic as well. Oh, so what do we gain by this? Well, we gain a structure that doesn't depend on how we interpret. We can use state T right now to the structure. But also one thing is that we get meaningful types. You might notice that a lot of people learn in Haskell, first thing is how to build a parser combinator using state T. So state T is often used to make parsers. But the problem is that state T, maybe is not a reg expression type. Because it's too, we call it too big. For example, this type, we can't use this so this is not a regex type because some things we can express in this monad are not regular expressions. For example, this is not a regular expression. There's no corresponding thing that has this. The regex, but alt prim is a regular expression type. There's some caveats. You do laziness and recursion. For the most part, it's a expression type. So we can work with a regex type and then interpret it or run it in state T. So the benefit is that we have a type that we know is a regular expression. Instead of using state T directly, like a lot of tutorials use for parser combinators, we can just work directly with the expression type. So this is, we know it's a type. We interpret it to expression, to state T. This gives us meaningful types because I can't just say that state T string maybe is my regular expression type, is my parser type, because it's too big to be a parser, it's too big of a expression. But alt prim is exactly the perfect fit for the type, for what it means and what we can do with it. And going over the other pattern, the other structure, the other way of handling all the free structure is we can actually pattern match on it, right? It's not magic. There's no magic here. It's just the regular data type. We don't need to use the running function. We don't need to use fold map. Imagine going to a first Haskell class and saying, to map a list, use fold map, right? It's not something you would tell a first year Haskell student. You can always use, the beauty of Haskell, you always have direct pattern matching. So we can even implement this. So if state T is cheating for you, if you think it's too much cheating, using the whole library to do most of the work, we can do the work ourselves without the cheating. And we can just do that by normal Haskell pattern matching. I think one thing great about this is that this is normal techniques everyone knows from Haskell, just learning after the first month of Haskell classes. So the alt type is actually just a normal ADT with the essential type. In this form, it's a little opaque, but I'm going to write it in another form. It's just alt is a chain of alternations. It's like a linked list. It's like cons and nil. And alt type is a chain of apps. So this is like a linked list of linked list like alternate. So alt is a chain of choices, and alt type is a chain of apps. This is the way I internalize it, how I think about it. So if you think of a list, we have cons and nil. This is also a linked list that has cons and nil, but the cons and nil cells are more suited for what we're doing. So this is just what the type, this is how you can think of type. Alt is a list of alternatives, and each alternative is a list of applications, of chains of applications. So writing this is not that bad. We can just use asum. So this is our function. We use asum on asum for maybe. We'll find the first just. We'll find the first just in a chain. We need to match chain all the options. So, and then there we need my match chain, we need to parse an alt f onto a string. So a single option onto a string. This one's a little trickier, but we can leave a hole here and GHC will tell us what we need to go there. And I'll promise you that this function is a lot easier to write than it looks because the type system. This is what it ends up being. But it's just type Tetris. A lot of this just happens naturally when you look at the types and what matches where. So this match chain will run a single choice on a string to get maybe A. If we match on the con cell, which is app, then if the string's empty, we get nothing. If it's not empty, we match on the prim we want to match on. They run match up. We recurse back to the first data, the first function. So I think this part, if you follow logic, then it makes logical sense. The hard part is writing it right. But actually, writing isn't that hard either because most of this is self-evident from the types. Just use the type Tetris. You only get a lot of it just matches itself just from filling in type holes successively and narrowing down your options. So this works as well. I'm not interactively coding, but you can trust me. You can pretend I'm writing this down, and it's interactive. It does work. So what happened here? So what do we gain from using this method? We get to now use Haskell 101 techniques. We can even rewrite our regex types. If you want to do like optimization on our types, we can optimize it directly by using pattern matching. This is just normal pattern matching, right? Anyone can do this. Everyone can pattern match. Anyone can pattern match and rewrite types. There's nothing special about it. And also, something nice is that we get a what I call a normalizing representation, where it kind of forces equivalent regex to be equivalent in structure. This means that if things mean the same thing, then they have the same structure. For example, if we implement this naively using a data ADT, this structure here is not normalizing because if we have A or B or C, it's not the same as A or B or C in this data type, if you can see. And this is helpful because you can imagine having a bug where you treat these two things differently, even though they're the same, right? You don't want to treat this differently than that. You don't want to treat this differently than that. You want to treat them the same way. Using the free structure forces that same representation. So using free structure means that you'll never treat the same type, the same structure in a different way. So this is not a free structure, even though it might look tempting to be a free structure, because it's not normalizing. Because we can treat this value is different than that value, so it's the difference is apparent to us to use nakedly. But if we use a free structure, it forces us to erase this difference, and this difference is no longer normalized to one constant same structure. So we aren't allowed to treat these differently, and it prevents a whole class of bugs. So in the end, the moral is free your mind. So this my problem is modeled by some commonly occurring structure over some primitive base. So my problem here was is really well modeled somehow by the alternative type class over some primitive character type. This is our perfect thing. This happens actually a lot more than this happens a lot in Haskell, and it's kind of all about seeing it in this way. So then the next time you have a problem that came out by some structure over some base, try thinking about what this common structure is and seeing if there's a free structure. If it comes from a type class, you can use a free structure. So in the end, the overall feature is that you can use a function combinator to enhance your primitive base with that structure. And if that structure comes from a type class, you can just use the free structure. And the free library has a bunch of them: monad, comonad, just go free, alternative, applicative, and transformer has a few too. There's a lot of free structures out there. For most type classes in Haskell that you use commonly that are in this form, I would say most of them have a free structure. So most type classes that you might get structured out of. These are very common abstractions. You can use a free structure to get that structure, get that functionality for free in this way. You can get it in a way that gives you pattern matching, so you can use his normal ways to process it and program transform. use a way in the folding way to like offload your work to another applicative or alternative or structure, right? We offload all our work to state T in the first method. So we can use all things. If we can, if a problem is modeled by some structure or some primitive base, and that structure is a type class, we get the free structure. We have all functionality we get for free. We can offload the work to someone else, and we can even use free program transformations. And that's yes. Is there a question? Okay. Okay. So this is the end of the talk. I have some extra resources. This talk is based on a blog post that's here, and again, the slides are online. Some packages that have free structures are the free package. This has a great name. Fun Comments has a bunch of them. This is my package. I organized a lot of them into a single package. So I spent the last month or so finding all the features I find in the whole Haskell ecosystem, all of them in free transformers, and I put them onto one package to make it easier to find and use together. And this post here lists a lot of them. And talks about a lot of them. If you want to look at different free structures, what they can give you, you can look at this post. But really, everyone in Haskell knows the type classes, right? They know functor, monad, applicative, the alternative. Everyone's familiar with these structures, these type classes. So anyone can really take advantage of this, I think. Anyone who knows what applicative is can use a free applicative. Anyone knows alternative can use free alternative. Anyone who knows how monads can use free monad. It's just a matter of finding your problem as some base type over some common structure in Haskell. And thank you for listening.